Hey folks, in this next video we're going to look at problems involving the concept of work. So just 3 to start us off. So this first one's about dragging your sled, a certain force, a certain angle, and a certain displacement. So this one is just like about as simple as it gets for the concept of work involving a calculation. Sorry, I forgot to show you the screen. All right. So we are pulling with a force of 25 newtons that is directed 30 degrees above the horizontal, and the displacement is 50 meters. And so we're calculating work. So this is as simple as that. Work equals FD cosine theta. So work equals 25 newtons times 50 meters times the cosine of 30 degrees. And so that's 1,083 joules. Just make sure your calculator is in degree mode at all times in physics. A diagram is very helpful in most situations involving work. All right, next up is a ball drop. We know the mass of the ball. We know the height, how much work is done on the ball by gravity during its fall. So if the ball is dropped, then the force of gravity acts downward on it, and the force of gravity has a magnitude of mg, and then the ball is going to fall in that same direction. So force and displacement have the same direction. Work is FD cosine theta. In this situation, the force that we're talking about is the force of gravity, and that's equal to mg. So the work is equal to mg times d times the cosine of the angle between those two vectors. So we have 0.5 times 10 times 15 meters. Okay, so mass times g times 15. And then the angle, if both vectors point in the same direction, then the angle is 0 degrees. Cosine of 0 is 1. That's the maximum value that the cosine function can have. And so that happens when the two vectors are in the same direction. So this answer is just going to be 0.5 times 10 times 15, and that gives us 75 joules. All right, so so far, our work amounts have been positive. So like work was done to increase the energy of the sled by the tension force, and again, work was done to increase the energy of the ball. That's the gravitational force. Next one is fully loading sharpening cart is rolling toward you. It moves at 6 meters per second. How much work must be done on the cart to bring it to a stop? So we're talking about like changing velocity. So I'm going to use the work done by the net force equals the change in kinetic energy, which equals the final kinetic energy minus the initial. Now, very importantly, we are bringing this cart to a stop. So we will never stop looking for these words and phrases that tell us that something's zero. The final kinetic energy is going to be zero because the cart's going to be at rest when we're done. So that means that the work done by the net force is equal to the opposite of the initial kinetic energy. Now, in this problem, we are trying to find how much work is being done. So I'm going to leave sigma w as sigma w. We're just finding work. We're not doing FD cosine theta. That's equal to negative 1/2 mv naught squared. So that is equal to negative 1/2 times 30 kilograms times 6 meters per second squared. And so that is going to give us a negative amount of work. Work done by the net force is negative 540 joules. And so negative, again, just means that energy was taken away from the system that was having work done on it. And so the work was done on the cart to remove energy from it and bring it to a stop. So those are just 3 that get us started. We will make work a little bit more complicated in the last part of the unit, but that's about it for here.